We can see the title of his talk, Convex Bodies of Constant Width with Exponential Illumination Number. It is a joint work with Andriy Prymak and Andriy Bondarenko. When you're ready, just activate your microphone and talk.
Thank you. I'm just a little too early, I guess. So I don't know if I get any extra time if I start early. Anyways, I'll just start slowly because there may be some people joining closer to 8:10, so I'll begin very slowly to account for that. So it's a joint work with two other Andreys. We have a different spelling. If you noticed, my name has a different letter in the end. That's because at some point they changed the way Ukrainian is written, translated into English, and I obtained my first passport in Ukraine with Y in the end. And then they changed the rules. And I was not lazy to write a special request to keep the same spelling of the name in the next passport. But the other Andriy Prymak is younger, so it was just his first spelling. But Andriy Bondarenko was lazy and didn't request to keep that same thing. So this is the story why I have Y in the end, but the other Andriys have I in the end. Okay, so my talk is about some problems connected with Borsuk's number. So all of this was motivated by study of Borsuk's number, which is the for any positive integer n is the smallest value f of n, smallest integer f of n. So that if you take a set of a diameter 1, you can cover it by f of n pieces of smaller diameter. So you can think here of covering, or you can think about splitting into smaller pieces. So it's easy to see that if you take a regular simplex, then you have n+1 points which are equidistant. So, and this is the diameter, that distance is the diameter of the set. So if you want to split into two smaller pieces, you cannot cover, or you cannot have two vertices in one piece. So this number is at least n+1, and Borsuk asked if it's equal to n+1 for all n, which turned out to be a very interesting question. So he proved that this is true. Well, it's trivially true for one-dimensional case, not too hard for the planar case. Then later, Perkal proved that this is also true in the three-dimensional case. So any set of diameter 1, we can split into 4 smaller pieces in 3 dimensions. And it was a big question, what happens if the dimension is large? So eventually, what was done was an asymptotic lower bound, which grows faster than polynomial. So it's a constant to the power root n, with the first result was by Han and Kalai with one value of the constant, and then Rygorodsky somewhat improved the constant. And this shows, of course, that when n is large, the answer to Borsuk's question is going to be negative. And right now, there is a separate story which can take quite a bit of time to discuss. So I'll just mention that the smallest known value of n, for which f of n is bigger than +1, is currently at 64, but there was a whole story, and you can spend separate slide discussing those results. So finding smallest n where it's big is interesting, and very interesting what happens in 4 dimensions. So that's Borsuk's number, and we kind of discussed the lower bound here. So for the upper bound, we have the following: like when n is very large, f doesn't grow faster than root of 3/2 to the power n. And this was first obtained by Schramm and later by Bourgain and Linder-Strauss. And their approaches are different, and we'll discuss them. So just an illustration, like what you could do with a triangle in, like with simplexing the plane, right? So one approach, you could shrink the triangle slightly and shift around a little bit, so you can cover the triangle by 3 slightly smaller triangles. And that makes sense because you're kind of covering the set with something self-similar, and it could be efficient to, if what you're covering with resembles the same shape. But alternative approach, you could cover with disks of diameter smaller than 1. And that also makes sense because if you fix a diameter, then a set of the biggest volume is going to be the disk of that diameter. So that's also a natural way to approach this problem. So we will talk now about Bourgain and Lindenstrauss results, and they do exactly this approach. So they study the following number, G of n, which was probably introduced by Grunbaum in the 50s. That's the smallest number of balls of diameter smaller than 1 needed to cover arbitrary set of diameter 1 in the n-dimensional space. And we clearly have this bound, like because each ball of diameter smaller than 1 is of diameter smaller than 1. So it's an upper bound on Borsuk's number. And prior to Bourgain and Lindenstrauss, there were upper and lower bounds on this number by Rogers of the order √2 to the power n, and by Denzer, who showed that there is some small exponent slightly bigger than 1. So the behavior of G of n is exponential in the dimension. And then in 1989, Bourgain and Lindenstrauss, they showed √3½ to the power n from above, and they improved the value of the exponent for the lower bound in Denzer's result. So that's the result of Bourgain and Lindenstrauss. So again, here we are covering with balls of diameter smaller than 1. And before we discuss another approach, as I had said, there was another result by Schramm. So before we do that, we need some definitions and some concepts. So we need the concept of illumination. So if you have a convex body, and convex body is a convex compact set with non-empty interior in n. So it's non-empty interior means you are essentially in n-dimensional situation. You cannot bring your set into a subspace of smaller dimension. You take a point on the boundary and take a direction psi. So that point will be illuminated by the direction psi if you start a ray at that point in that same direction, and if that ray intersects the interior of the set, then we say that that point of the boundary is illuminated. So here in this example, all the blue points are illuminated, but say this one, the black point here, and all the others will not be illuminated, because then if you do this rays, they will not be inside the body. So that's illumination. So we illuminate a point if that direction crosses the point into the interior of the body. Now, the smallest number of direction needed to illuminate every point of the boundary, we will call I of k, and we'll call this illumination number for that convex body k. And finally, h of k is going to be the smallest number n that we can cover k by n smaller homothetic copies of k. So we shrink the body a little bit, and we can translate it afterwards. So that's essentially what a smaller homothet is. We don't allow rotation, we just shrink it a little bit, but we keep all the proportions essentially. So Boltyansky showed that the illumination number is always equal to the this number, to the number of smaller homothetic copies required to cover the body. And the intuition, why is this true, is the following, that if we return to our example, if you have that body k, you shrink it a little bit k prime, and you move it in the direction opposite to the illumination vector, you see that it covers almost exactly that blue part that's illuminated. And then certain compactness argument, because things are compact and finite here, allows to prove the equality. So it's equivalent concept. If we want, we can work with illumination. And here I consider the illumination by essentially parallel beams of light. You can also do external point sources and illuminate from a point source, but then those directions won't be parallel. But that concept is also equivalent to this concept. So this is equivalent to covering by smaller homothetic copies. But for our purposes, it's going to be more convenient to work with illumination number than with covering by smaller homothetes. However, for the purposes of the Borsuk's number, for covering a set with smaller copies, it's enough, right? So we will be working with the illumination number. We just need to know that these things are equivalent. And next concept that we kind of need is that of convex bodies of constant width. And that's a very easy thing. If you take a convex body, take any direction, any line, and project it onto that line. If what you are getting, it's going to be a segment if it's a convex body. So if the length of that segment doesn't change, no matter how you rotate the line, we call that body a body of constant width. So a trivial example is a ball, of course. If you have a ball, it doesn't matter where you project it, on which line you project it, you get length, same length. But there are non-trivial examples, and as a matter of fact, there are many convex bodies of constant width. And what's more important for us in the context of study of Borsuk's number is the following statement, that if you take any set of diameter 1, then you can find a larger, by inclusion, by set inclusion, you can find a larger convex body of constant width, which is going to have the same value as the diameter. So we can embed any set of diameter 1 into a convex body of constant width 1. So say if you take equilateral triangle with length 1, side length 1, then what you can do, you can draw like the arc. So see, this one vertex as a center and draw this arc of a circle of radius 1 and do it 3 times. What you are getting is probably the most well-known non-trivial example of a convex body of constant width, which is Riemann triangle. I'm sure I'm not pronouncing that name correctly, but that's going to be a very known example. So now it doesn't matter how you look at this Riemann triangle, its projection is going to be the same length. And you can go to YouTube and even find some interesting things like there are bicycles which have Riemann triangles as wheels, and they work just as well as usual bicycles. So that's interesting. Anyways, so for us, so what happens for us if we are studying a covering of sets of diameter 1 by sets of smaller diameter, we can always enlarge a set of diameter 1 to be a convex body of constant width 1. So if you look at Borsuk number, and rather than taking sets of diameter 1, you replace it, that set with set of convex bodies of constant width 1, you're going to get the same definition. And so it's enough to be covering convex bodies of constant width. So that way we can define the following quantity h of n, which is the largest value of h of k, the number of smaller homothetes, or alternatively, because of the equivalence, you can think of illumination number, among all convex bodies of constant width. So you take k, a convex body of constant width, and you look at the number of smaller homothetes needed to cover it, or you look at its illumination number, and then you take the supremum over all convex bodies. So that way you get convex bodies of constant width. That way you get this quantity h of n, which is going to be bigger than f of n. So it's another approach to obtain upper bounds on Borsuk's number, is to work with illumination number of convex bodies of constant width. And that was exactly what was done by Oded Schramm in 1998. And he got the same upper bound as Bourgain and Linder-Strauss did. Now, in the other direction, remember that for the Bourgain and Linder-Strauss problem with balls, there was an exponential lower bound. Here, the only known lower bound on this quantity h of n was the same as for f of n, and that was the sub-exponential. You have a constant to the power root n. And Gilles Calais in 2015 asked if you can if you can prove an exponential lower bound for this h of n. We have upper, do we have lower? And that's precisely the main result that we obtained. And we answered the question of Calais in the affirmative by showing that there are convex bodies of constant width for which the illumination number behaves at least exponentially. So this is our main result. Notice there is the minus here. So I just prefer this way of writing. Cosine pi over 15 is smaller than 1, of course, but we have negative here. So that's our main result. And it's, I'll just outline the ideas of the proof. So the main geometric ingredient, what we're going to be doing is we'll be using this remark that if you have a set of diameter 1, you can always extend it to a convex body of constant width 1. So we will first build some set which is going to have diameter 1, and then we'll be extending it to a convex body of constant width. So that set that we're going to be building will be built from certain basic elements. So a basic element is going to be the following set QXA, which is depicted blue in this picture. So X is a point on the sphere. So we take unit sphere, we take a point on the unit sphere and a fixed angle alpha. And basically we take that point and we take the set of points Y from the sphere, which are at the distance 2 cosine alpha from the point X. So that actually means that you are considering a cone. So if you take if you take X, vector X as an axis, and you just take angle alpha from there and rotate, you're going to get a cone. So essentially we're taking the apex of that cone and we're taking the base of that cone. So under the condition alpha at most pi over 6, the diameter of this base of the blue set is going to be smaller than 2 cosine alpha. So actually the diameter of this Q is going to be then equal to 2 cosine alpha. So this is what is important here. So this is our building block, this blue set Q of X alpha. And we need some more notations. So theta is going to be, for the points on the sphere, is geodesic distance between vectors, between points X and Y. And otherwise, it's just the angle between the directions X and Y. And Cx alpha is a spherical cap. So if you take a point X on the sphere and you consider all points Y on the sphere, which have the spherical distance between them at most alpha, you get this Cx alpha. That's just a spherical cap, like a spherical ball, but we will call it cap. So the main lemma, the main geometric lemma that we have is that if you take this basic set Qx alpha, and if it's contained in a convex body K of the same diameter, so if the diameter of K is also 2 cosine alpha, then this X, this apex of the cone has to be in the boundary of this body K. And if you have a direction that illuminates that point of the boundary, then it must come from a certain cone, from a cone centered at minus X and of certain angle pi over 2 minus alpha. So that's not very hard to prove. Actually, this picture is pretty much the proof. So like if you take, if your angle theta is not in that cone, then you can look at two-dimensional section that contains your point X, that contains this vector psi, and then you can find Y from the base of the cone so that the angle between yx, between the line yx and the vector c is bigger than pi over 2. And once you find that, then you can kind of, because the body has certain diameter, it's inside this green ball. So the point y is in the body, yx is the diameter of the body. So you can draw the ball of this radius, and which will bound your convex body. So the interior of your body has to be inside this green, bounded by the green arc, but your illumination vector, psi, is in the other half plane, so it misses the interior of the body. So this is kind of the proof. So it's very simple geometric proof, but this is what we need for to perform the subsequent arguments. Now, the other ingredients that we're gonna need are the following. So our set, it's not enough just to take one cone. We need to have many cones, and they are essentially defined by the angle alpha. So we'll keep that angle the same, but we will take the union over different axes from this. So we will fix some discrete subset of the sphere, which will be the set of apexes of our like skeleton set of those cones and we take the union of those basic sets. So to control the diameter of the result, it turns out that we need certain separation between the directions. So for the case of this W of X, so which is second part here, we just need basically the directions between all the points need to be 6 alpha separated. So if we have 6 alpha separation, then we can guarantee bound to the diameter, and the proof of this lemma is just triangle inequality for the geodesic distance. So it's not a big deal. And now we're gonna need that discrete subset of the sphere. So now we need a good configuration of points on the unit sphere. So we get that using the following result. We get that from the following probabilistic lemma, that if you fix two angles, psi and phi, which are strictly between 0 and pi over 2, then you can find a good collection of points on the unit sphere. And the cardinality here is sort of optimal because the spherical area of a cap of radius phi is roughly 1 over sine phi to the power n. So and that is kind of almost the best you can expect, because the condition B here is that we cover the whole sphere, and any point of the sphere is covered by at most linear number of these phi spherical caps. So we have psi separation between the centers of the cap, and we have phi covering of the whole sphere, which is good in the sense that each point of the sphere is not just covered, but it's not covered many times. So this is very important. This linear factor over here is what allows us in the end to control the illumination numbers. That's the important part over here. Okay, so this probabilistic lemma, like if we don't impose A, it was known. It was the result of Borodsky and Winshire, who adopted the ideas of Erges and Rogers to the spherical case. And it's just a careful counting of probabilities. But the construction is just take uniformly distributed points on the sphere, and you can show that with high probability, take proper number of uniformly distributed points on the sphere, and with high probability, they will satisfy the condition B here. So we only need to ensure the condition A is satisfied, and to do that, we just kind of count the number of bad pairs. So we estimate the number of pairs which are too close, because what we want to do, we want a separation between the centers of the caps. So we count the number of pairs that are too close, and we can show that under these conditions, that if psi is strictly smaller than phi, then the expected number is not too big. And if it's not too big, we can then, so it's at most n prime over 4. And then you can remove a point from each pair, and then you'll get a good configuration. So that's the idea. So basically, the construction is you take uniformly distributed points. You may have to remove some part of them, but with high probability, uniformly distributed points with possibly some of them removed are going to satisfy the results in this lemma. Okay, so after that, our theorem is just putting pieces together. So using probabilistic lemma, we take alpha equals pi over 14. And pi over 14 comes because you need strict inequality here. And if you recall that in our geometric ingredient, we are covering by the caps of radius pi over 2 minus alpha. So 6 alpha plus alpha needs to be smaller than pi over 2, basically, smaller or equal than pi over 2. So this is where pi over 14 comes. And then you just combine the pieces together. So you just combine the probabilistic lemma, the separation lemma, and the geometric lemma. You get a good skeleton. And then, because each point, if a point is illuminates each vertex, so each vertex of each apex of our cones cannot be illuminated by too many directions because of the covering condition in the part B. So after we posted the preprint of our work on arXiv, Alexey Glaziri noted that you can improve, you can use the same construction and just slightly modify it to somewhat improve the numerical value of the exponent at our result. And you can just, what you do, that you keep the apexes on the same sphere, on the unit sphere, but you take the basis of these cones from a slightly smaller sphere, and that allows to push a little bit the separation condition. Now, another result, I'll just very quickly mention the other result, is that we obtained a new lower bound on G of n. So G of n was the smallest number of balls of diameter, smaller than 1, needed to cover arbitrary set of diameter 1 in En. So Bourgain and Lindenstrauss method gives this value, and we obtain the following value. And as you can see, there is a significant improvement here in the exponent. And the proof is very simple. You just use probabilistic lemma and use the separation lemma part I, which I didn't discuss, but it's very short. It's like 2 lines proof, essentially, from these ingredients that we have, and we get a better value. And I could even say that perhaps it might actually happen that this value of the exponent is sharp. So the conjecture that I want to say is that the Borsuk number should be bounded from above by that value, by 2 over root 3 to the power n. And this would be the easiest thing to achieve, because for Borsuk's question, you have a lot of flexibility in terms of the things you can cover with. You can cover with any sets of diameter 1. But there are 2 related questions. You might be able to prove this either using smaller homothetic copies of bodies of constant width. So you might be able to prove this bound for H of n. And it would be very interesting, but probably the hardest, if the following question has a formative answer, if we can establish upper bound with the exponent 2 over 3 for covering with balls of smaller diameter, for covering an arbitrary set of diameter 1 with balls of smaller diameter. But I do believe this is a reasonable question to ask, because this value 2 over root 3 appears very naturally, because it comes from pi over 3, from sine of the half of that. So it's a very natural thing, but I'm not sure. I'm quite sure that f is bounded by that value for the Borsuk, but I'm not quite sure, but it could happen that what we found, this constant that we found for the balls, is actually sharp. So thank you.
Thank you. Your exposition has been very clear. I remember Andriy Bondarenko 10 years ago in Kiev. He was stunning. He was talking about Borsuk's conjecture. And
right. So I didn't say this, but his result was 65. So what he did, he proved that he found that for n equals to 65, f of 65 is bigger than 66. Well, actually more than 60.
Yes, it
but
was
this
an
was
incredible result.
Yeah, this is what he did. But there was I don't remember the last name right now, but there was then a follow-up paper where it was pushed down to 64 dimensions. Yeah.
Okay. So, are there any questions for Andriy? Any comments?
I have a naive question, Andriy, maybe not very much related, but as far as I remember, there is a general open problem of covering of unit sphere in a RAM by randomly dropped caps. Could it be kind of related to what you are doing, your probabilistic argument?
Well, if you're using random, then this is it's not open question. If you're covering by distributed, then it's very clear what you can do, and this is what we are using. I think the question is, what if you want a structured configuration? Because if you are not using random configuration by structured configuration, you may hope for much better results. So if you're using random, it's very clear. You just take the volume of the cap, 1 over the volume of the cap is the answer, asymptotically.
Okay, yeah. Thank you very much.
Yeah, you're welcome.
Other questions? Well, thank you to our speaker. It was a wonderful talk. Thank you very much.
Thank you.